for 6.1 number 12, we're supposed to find the area of the region bounded by the curves y equals e to the x, y equals 12 minus e to the x, and the y-axis. And if we look at this here, we have the curve that we should all be familiar with, the line, the curve e to the x, that crosses the y-axis at 1 and approaches 0 as x approaches negative infinity. Negative e to the x would flip everything across the x-axis. So what was 1 is now negative 1. What was approaching 0 is still approaching 0, but it's approaching 0 from the bottom. What was going to positive infinity is now going to negative infinity. And this is important because what we have here is 12 plus the negative e to the x function right here. So this 12, what it does is it shifts every point up by 1 unit. Okay, so I'm going to try to exaggerate this. This negative 1 plus 12 ends up being 11. So this is 11. It has its horizontal asymptote at 12 now because it used to have a 0 horizontal asymptote. And you add 12 to that and you get 12. Okay, and then it comes down like this and goes towards negative infinity. Okay, and the e to the x function fits in here like this or something like it. Right now we're just sketching, so it doesn't really matter. But you can also get this information by graphing it on your graphing calculators, whatever kind you have. But, and the bonus of that is the graphing calculator will also solve for this point of intersection here. And we're actually going to need to know this point so that we know the bounds. Okay, so why don't we solve that right now? This right here is y is equal to 12 minus e to the x, and this curve right here, that's still the same curve. This curve right here is y is equal to e to the x. Okay, so they share the same point when the two functions are equal, when y1 is equal to y2. Okay, so or when 12 minus e to the x is equal to e to the x. We could add e to the x over to both sides and we'd have 12 is equal to 2 e to the x. Divide through by 2 and we have 6 is equal to e to the x. Since x is in the exponent, what we need to do is use e's inverse function, which is the natural log function. So we will natural log both sides, and we get the natural log of 6 is equal to the natural log of e to the x. And the natural log of e to the x is equal to x times the natural log of e. And that's equal to the natural log of 6. The natural log of e is equal to 1. So that means that point of intersection occurs when x is equal to the ln of 6. Also, we were told that the y-axis, or when x is equal to 0, is another boundary. So this area right here is the area that we're interested in. X goes from 0 to the ln of 6. And we could take one of those rectangles, so we're going to add up a whole bunch of rectangles, infinitesimally thin rectangles, right? The height is going to be this top function minus the bottom function. The width, if you notice, is going to be a small portion of the x-axis. So we call that delta x. And if we put that together, what we have then is our delta area, or our small piece of area, is going to equal the height, which is the top function, minus the bottom function, times delta x. And since we have the thickness in terms of delta x, we know we have to integrate with respect to delta x. So we use these functions in terms of x. And our top function was the function 12 minus e to the x. So we have 12 minus e to the x minus the bottom function, which is e to the x. and all of that is still multiplied by delta x. Okay, so this is our small chunk of area. And we can simplify that more and say our small chunk of area is equal to 12 minus 2e to the x, delta x. Now, as we let x go towards 0 to make these infinitesimally small widths, we would be adding up and approaching an infinite number of these rectangles. And by adding up an infinite number of rectangles, what we get is an integral. So, and since the boundary starts here in terms of x at x equals 0 all the way to x equals ln of 6, our bounds of integration are going to go from 0 to ln of 6. And we'll be integrating those small areas, or adding up those small areas. Okay? And this is one of our basic antiderivatives. We get 12x minus 2e to the x, and we'd evaluate that from 0 to the ln of 6. So that's going to be 12 times the ln of 6 minus 2e to the ln of 6. Okay, that's our first term using the fundamental theorem of calculus. F of b minus f of a. So now we plug in 0 and we get 12 times 0 minus 2e to the 0. E to the 0 is just 1, so we have a negative 2 here, and this is 0. The negative 2 pairs with this negative, and we get a plus 2. E to the ln of 6, or e to the ln of anything, is that anything? So this is 2 times 6, so that's minus 12. And this is still just 12 times the ln of 6. Okay, so now we have 12 ln of 6 minus 12 plus 2, or 12 ln of 6 minus 10. Box our answer. There we go.